Alright, so now I wanted to show you some mathematical models we use that come from our graphs to represent constant acceleration. Okay, so again with constant acceleration we have a position time graph, a velocity time graph, and now we also have a acceleration versus time graph, right? So if you recall, well, let's start with the acceleration graph. It has to look like this. Now, this acceleration could be positive or negative. I decided to make the acceleration positive just because it's a little easier just to start with. And you'll notice that this area has meaning for us, right? Acceleration is measured in meters per second squared. That's the standard SI units, meters per second squared. Time would be in seconds. When you multiply meters per second squared times seconds, you get meters per second. And in physics, areas of graphs are changes in things, right? So this has to be a change in something that's measured in meters per second. Well, it turns out that has to therefore be a change in velocity. So the area of our acceleration versus time graph is our change in velocity, right? And it doesn't have a special name like change in position does, but it's still valuable nonetheless. It's going to be like our final velocity minus our beginning velocity, or a velocity at a later time minus a velocity at the earlier time. And that's going to be equal to A, acceleration, times time, because this is a rectangle shape. So acceleration times time gives you the area of that rectangle, right? And if I solve this for final velocity, I get acceleration times time plus my initial velocity, v naught. Okay, now what I love is so our velocity graph actually has a slope, and today in class we discussed, at least some of my classes, periods 3 to 6, and then earlier this week, I think in my other periods, or early last week, we talked about how the slope of this graph, so the change in velocity, right, divided by the change in time, right, slope of v versus t graph. Well, we agreed that that was our acceleration, which is going to be change in velocity, not change in position, change in velocity, divided by change in time. So that's like a later velocity minus a beginning or an earlier velocity divided by our change in time. And this has the symbol A with a vector symbol because acceleration has direction to it, right? And you'll notice what's kind of cool is this equation here is the equation of this line. You know, this is the intercept v naught. This is the later velocity v final. So this is in the form of y equals mx plus b, right? For that velocity graph. So this is the equation of the line on our velocity graph, right? And we can also, here I'm going to do this in a different color. I can find this area here, which is a triangle, plus this area here, which is a rectangle, right? So you'll recall from the last unit that the area of a velocity versus time graph is going to be displacement, right? So, all right, displacement, kind of a cool word, which is going to be our change in position, right? And you'll notice this part here is just v naught times t, right? That's the rectangle part. Try to write that better. V naught t. So that's that little rectangle. Now let's deal with this part, that triangle. Going from here to here, that's our change in velocity, right? So plus, we got to add that triangle part. So that triangle is going to be 1/2 change in velocity times time. Now, over here, it would help to recall our definition of acceleration, change in velocity divided by change in time. And if I solve that for change in velocity, I get a change in time. Now, change in time is going to be the same thing as time for us. We're just going to use the symbol t for change in time. So we're not going to distinguish in this example. Therefore, change in velocity, I can simplify and just say it's equal to at. And that'll make this a lot simpler here, okay? So what I'm saying is this part here, I'm going to replace, okay? So this part right there, I'm going to replace that with a times t. The other stuff's going to stay the same, so I'll just rewrite it. Displacement is initial velocity times time plus 1/2, and then I still have another t over here, okay? This is a vector here, and that's a vector there. Okay, when the dust settles, I'm left with displacement equals initial velocity times time plus 1/2 at squared. It's kind of nice. And I can go further. Displacement is final position minus my beginning position, right? And that's got to equal initial velocity times time plus 1/2 at squared. And I'll even go one step farther here. Okay. So I'll say, I'll just add initial position to both sides. I get final position is going to be equal to initial position plus initial velocity times time. This equation has some beauty to it, plus 1/2 at squared. So this equation actually assumes constant acceleration because you notice it comes from graphs that assume constant acceleration, right? So these are kinematics equations that assume constant acceleration, okay? And this equation here, guess what? It's the equation that represents this beautiful curve on our position graph, okay? So in other words, that curve, you notice it's a parabola, and you'll notice that you have a square. Whoops, there it is. You have a square right there to make that parabola. And your initial position is right here, right? Your final position is what we're talking about here when we graph, okay? T is right here. And again, the equation of that curve is going to be x final equals initial position plus initial velocity times time plus 1/2 at squared. So I find it interesting and beautiful how all these things connect together. Again, the slope of our position time graph, I should probably remind you, in a curve situation like this, notice that the slope's getting steeper. So you'd have to use slopes of tangent lines, right, to find a slope. And that slope is changing. But I can remind you that the slope still of a position versus time graph, or of the slope of the tangent lines in this case, is going to be our instantaneous velocity, because it's changing velocity in this case. I'll write instantaneous. Which is, in calculus language, it's going to be the limit as our time gets closer and closer together between the 2 points we're using to take the slope of change in position over change in time. And this turns out to just be the slope of lines that are tangent to the curve. So each tangent line can give you an instantaneous velocity wherever that tangent line touches the curve. If you remember that a tangent line is a theoretical concept where a line just touches a curve in one spot. And so you can use slopes of tangent lines to figure out instantaneous velocities at different moments in time on a position time graph. Anyway, I hope that helps. Quick review, slope of a position time graph is our velocity. Slope of our velocity graph is our acceleration. The area of our acceleration graph is our change in velocity. The area of our velocity graph is our change in position. So, ghetto language, position is where you at. Velocity means how you be moving. Acceleration really means that how you be moving is actually changing. Okay? So don't get confused. You could be at any position with any velocity and have any acceleration. Just because you have zero acceleration doesn't mean you have zero velocity or you're at a zero position. Likewise with the others. They're independent of each other, but they're also intimately connected to each other. Anyway, I hope you're having fun enjoying this, and thanks for watching. Have a good day.